So hello everyone, in this video we're going to solve another DP question based upon strings, and it's called count binary strings, right? So let's look at the objective of the question, which are these two lines over here. Let's take this to the page, and if we read them out, it says that you are given a number n and you're required to print the number of binary strings of length n with no consecutive zeros. Right? So what does the question mean? What does the question mean? It says that we have to print the number of binary strings that are possible of size n, which would be the input, that such that they have no consecutive zeros. To understand this a bit better, let's take a sample input case, right? So let's suppose for input I have n equivalent to 3, right? So I have to give the number of possible binary strings with no consecutive zeros. Let's take the first step and let's write all the binary strings that are possible of length 3. So the very first binary string would be 0, 0, 0. Then it would be 0, 0, 1. Then it would be 0, 1, 0. Then 0, 1, 1. And then 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, and 1. Right? So these are all the binary strings that are possible of length 3. This accounts for a total number of 8, which is nothing but 2 to the power 3. And it's because at each and every step, at each and every length, I'm getting two options. Either I can have 0 or 1. So two options are 0 or 1. And henceforth, if I give them 3 times the option of 2, I would get a total of 8, which are the number of binary strings that are possible, right? So out of these binary strings, what are the strings in which there are consecutive zeros? Those won't account for my answer in this question, right? Because we don't want consecutive zeros. Okay, so the very first string that we have over here, this cannot be my answer because it has 3 consecutive zeros. Then the second string also, it has 2 consecutive zeros. And then this one doesn't have any consecutive zeros, right? So it's 0, 1, and then 0. So 2 single zeros separated out. In between there's a 1. Over here too, the entire string only contains a single 0. Then over here, if you see, there are 2 consecutive zeros. So again, this won't be the part of our answer. And then if we look at last 3, over here too, we don't have any consecutive zeros. So the answer to the particular test case would be 1, 2, 3, 4, 5. So answer would be 5, as there are 5 binary strings that are possible which don't have consecutive zeros. Right? I hope the question is clear now, and I would wish that you try it out on your own and jump on the solution video after some time, right? So let's discuss the solution now. Let's discuss the solution again. As it is a DP question, there are 2 approaches to the question, right? So the very first approach would be recursive approach. Discuss about the recursive approach, and after discussing the recursive approach, we would apply the same idea behind the recursive approach to the tabulation that would create in DP, right? So in recursive, in recursion, the simple funda of include and exclude is something that we would be using, right? So at every step, at every length, I would give my string 2 options that the next digit can either be a 0 or a 1. Of course, there would be a condition over here, and the condition would be that if my previous digit is already a 0, I cannot have another 0. If my previous digit is a 0, I can only have 1. Right? So let's write what I'm trying to say. So let's suppose this is my length, and over here I write my last digit, right? So let's suppose my length, my current string is of course empty. My length at the starting for n equals to 3 would be 3, and my last is, let's suppose, -1 for now, right? Because my string is empty, so I don't have any last number. So for the very first call, I would have 2 options, 0 and 1. As there is no last digit, I can place both 0 and 1, right? That would give me 0. Now the length that I want is 2, because I already have a string of length 1. I would just want 2 more bits to continue to complete my binary string, right? And my previous is now 0. Okay, now for the call of 1, I would have my digit as 1, right? This is my digit, and I would have my length as 2 and my previous digit as 1. Again, over here, if you see, now that we have our previous digit over here, I would look at my previous digit, and if my previous digit is 0, I cannot have another 0 because the question says that they cannot be consecutive zeros. That's not allowed. So if I have my last digit as 0, I only have one option. And that one option is that I add a single digit 1 after my zeros, after all the strings that I have created, right? So over here, I would call for 1 because 0 is not allowed. I would have 0, 1 as my string, 1 length that's remaining, and my previous would become 1, right? Again, from over here, now my last digit is 1. As soon as my last digit becomes 1, after 1, I can apply both 0 and 1, right? Because I can have consecutive ones, that is allowed. Consecutive zeros is something that's not allowed. So over here, if we see, as my last digit is 1, I can make calls for 0 and 1 both. So I would get 0, 1, 0. The remaining length is 0. And as soon as the remaining length becomes 0, we just print this out, right? So this would be my first answer. Then it's 0, 1 and 1 again. So 0, 1, 1. And the length becomes 0. So this would be my another string. Right? So this tree is complete. This subtree is complete in recursion. Let's talk about this tree. Okay. So we have last digit as 1, 0 and 1 is the options that we have. Then 1, 0 becomes over here, and then one length 0. Over here it becomes 1, 1 with 1 length and 1 previous. Over here I can only call for 1 now. As the last digit is 0, I can only call for 1. So I get 0, 1, 1, 0, 1 with 0, and of course 1 over here. But as the length becomes 0, this would be my answer. From this point, I have two options, 0 and 1, as my last digit is 1. So I would get 1, 1, 0 from this end and 1, 1, 1 from this end. Right? So this is the recursive approach. What we are doing is we are including and excluding. Right? We are getting two choices. Right? Either one can be included or excluded. And if one is excluded, I would add 0. Right? And the condition in recursion is just that if the previous digit in the string is 0, I can only add 1. Right? And this gives me the answer. So if we look over here, these are the strings. These are the exact strings that we had over here, right? Okay, so now that the recursive approach has been discussed, let's talk about the time complexity. Of course, at every given step, we are getting two options. So the time complexity would be 2 to the power n. We have done similar kind of recursive questions in previous videos. And the time complexity over there also was 2 to the power n. Of course, it would have some conditions which would save some time, but of course the call would be made. Right? So this is henceforth really expensive. It's an exponential function. So let's jump directly onto DP now, right? Remember what we did was when there was 0 as last digit, we only called for 1, and when there was 1 as the last digit, we could call for 0 and 1 both. Right? So the same idea we would apply in DP and see how we can approach it with DP and get a better solution out of it, right? So the very first thing in DP that we do is assign storage, right? So we assign storage and meaning to the storage, of course. So, and the second step that we do is we recognize the direction, and the third step and the last step is to traverse and solve, right? So talking about the very first step now, we have to assign storage. Okay, so in DP, I would say I would take two 2D arrays, right? Two 2D arrays of size n plus 1. Right? Let's see why. The why and how would become much clearer after we have completed the third step of DP, which is traversing and solving, right? So as we had n equivalent to 3, that means the size of this array would be of 4, right? So I would write over here that size is n plus 1. And for an array of size 4, the indexes vary from 0 to 3. So we have indices like 0, 1, 2, right? Again over here 0, 1, 2, and 3, right? And if I draw conditions, this would be it, this would be it, this would be it, and then this would be it. Let's erase the extra portion from over here, right? So This is the DP array that we have. Now I would name these arrays as DP of 0 and DP of 1. Right? This was the step of assigning storage. Now what is the meaning of these storages, right? So in DP of 0 at index 1, what does this mean? So DP of 0 at index 1 means the number of strings that are possible, binary strings that are possible of length 1, such that there are no consecutive zeros. So whatever the question says, the number of digits that are possible, the number of binary digits that are possible which have no consecutive zeros and is of length of the index, right? So if we talk about DP of 1 of 2, DP of 1 of 2 would simply mean number of binary strings that are possible of length 2 which end at 1. So that's the catch, right? DP of 0 would only contain all the digits, all the count of the digits that end at 0. DP of 1 would contain count of digits that end at 1. So if there is a string 0, 0, that would have 2 as size, it would be over here, right? And if there is 0, 1, it would be over here. Right? I hope it's clear. I hope the meaning of DPs are clear. Again, DP of 0 of I, it's a standard, make a standard meaning. So DP of 0 of I, this would mean the number of digits, the number of binary digits or binary strings, number of binary strings that end with 0 of size I, right? Such that there are no consecutive zeros, right? So number of binary strings that end with 0 of size I. This is what DP of 0 of I means. And similarly, DP of 1 of I means number of binary strings that end with 1 of size I such that there are no consecutive zeros, right? I hope it's clear. I hope it's clear, right? So let's discuss now what would be the number of digits of size 0. Is there any digit of size 0? Is there any string of size 0? There is not. So DP of 0 of 0 would remain 0, right? As the size is 0, there does not exist any string at all. And similarly, in DP of 1 of 0 also, there is no string at all, right? So if the size is 0, it would be 0. Now this was our trivial case. Let's move on a step further, right? So what would be the size of strings when the number of strings when the size is 1? If the size is 1, what are the possible strings, right, that end with 0 and end with 1? So I would say the only two strings that are possible in this case when size is 1 is either 0 or 1, right? Is either 0 or 1. Understandable, right? So DP of 0 would contain 1 because out of these two, there is only one that ends at 0, right? And DP of 1 would also contain 1 because out of these two, this is the only one that ends at 1, right? These were our base cases. These were our trivial cases. So DP of 0 would always remain 0, and DP of 0 of 1, DP of 1 would always remain 1 because there exists only one strings each that end with 0 and 1, which are 0 and 1 itself, right, over here. Okay, so this was our base case. Now, if we see what would DP of 0 of 3 mean, right? DP of 0 of 3 is nothing but DP of 0 of n, because n was equivalent to 3, n was our input, right? So if DP of 0 of n is something that we are talking about, this would mean, by the standard definition that we wrote, is that the number of strings that end with 0 and have no consecutive zeros, right? And what would DP of 1 of n mean similarly? This would mean that that it would be equivalent to the number of digits, the number of strings that end with 1 such that there are no consecutive zeros in the string, right? So my answer to the question is number of digits, number of strings of size n such that there are no consecutive zeros. Wouldn't my answer be the summation of these two? If I add the number of strings that end with 0 and are of size n, and the number of strings that are of size n and ends with 1, and if I add them both up, I would get the resultant answer that we desire in the question, right? So my answer would be addition of these two, right? So dp of 0 of n and dp of 1 of n, if I add both of them, I would get my answer to the question, right? So it's quite evident that our answer would be on this side and our base cases are over here. That means my direction of solving the question would be in the forward direction, would be towards the right side. Understandable, right? Because we have the answer on the rightmost point, right? We add both of the last portions of the dp and we get the answer, right? I hope it's clear. So let's see how we can solve this now. So up till now, what we have discussed is the storage and the meaning and the direction in which we have to solve. Now let's jump on to the third point, which is traversing and solving. Now we know that these are the base cases, right? And for dp of 0 of 2, what would be my answer? What are the number of strings that end with 0 and are of size 2, such that there are no consecutive zeros, right? I can only add 0. If you remember in recursion, if I had my last digit as 0, I can only add 1 to it. But if I had my last digit as 1, I could add 0 and 1 both to it, right? So I could only add 0. I could only add 0 when my last digit was 1, right? This is what we discussed over here. If you look at the recursive tree again, we only added 0. We only added 0 when our last digit was 1. If my last digit was 1, then I added 0. If my last digit was 1, then I added a 0. If my last digit was 1, then I added a 0, right? I couldn't add 0 when my last digit was 0 itself, right? So when I am doing tabulation, keeping the same idea in mind, I would have 0 added to all the strings of length minus 1. So if I'm at length n, all the strings of length n minus 1 which end at 0, I would end at 1. I would add 0 to them. And this would give me the number of possible strings that are there of length n which end with 0. Again, let's iterate over this again. What I'm saying is, if I have 1 as my ending digit, then only I can add 0 to it. I can make 1 0. If I have 0 in front of any string, then I cannot add 0, because then it would give me consecutive zeros, which is not desired, right? So over here, if we look at this, in dp of 1 of 1, this signifies the number of strings which end at 1, right? So my dp of 0 would be equal to dp of 0 of 2 would be equal to dp of 1 of 1, right? So if I write this over here, my dp of 0 of any x would be equal to dp of 1 of x minus 1. This is what we derive. And this is similar to what we have done in the recursive tree. Okay, so let's iterate over this. I hope it's clear. So 1 would be over here as it is copied. And now if we talk about dp of 1 of x in the similar fashion, what we did was, when I had a string that ended with 0, if I take a darker one, okay, if I had a string that ended with 0, I could add 1 to it and I could make 0 and 1, right? If I had a string that ended with 1, I could add 1 to it and make 1 1. right? So I could add 1 to both when the last digit was 0 or when the last digit was 1. That means in my DP, when I have the numbers ending at 0 and 1 both, I can add 1 to both of them. So I would add this and this. That makes 1 plus 1, 2 over here. Okay. So what we did over here was that DP of 1 of any x is equivalent to DP of 0 of x minus 1 plus DP of 1 of x minus 1. Right? This is the formula for calculating DP of 1. This is the formula for calculating DP of 0. So if we do this for the last number, what we would get is 2 goes to DP of 0, right? As DP of x is DP of 3 and DP of 1 of x minus 1, which is 3 minus 1, is DP of 1 of 2, which is 2. So 2 comes over here, and then in DP of 1 of 3, we add both the numbers at second digit, so second index. So 1 plus 2, we get 1 plus 2 as 3, right? And now that our DP is completely filled, what was our answer? Our answer was addition of last two digits in the lastmost index. So 2 plus 3, which is 5, is our answer. For n equals to 3, 5 was our answer. If you look at the recursive tree, or if you look at the test case over here, 5 was our answer, right? I hope it's clear. So another thing that we should observe over here is that when we're traversing and solving, the number of states that we require are just 2. We want a current state that we would fill the answers to, and we want a previous state that we would fetch the answers from, right? For DP of 2, if you look at these formulas itself, for DP of x, we just need x minus 1, right? DP of x would need x minus 1. So we only need one step behind, right? The previous step is all we require. So do we need an entire array for that? Do we need an entire array to solve for digits when we could only get, we only have to fetch the previous 2 digits, right? We don't have to. So what we can do is we can space optimize this problem. We can space optimize this problem by using variables instead of an array, right? That would move our solution from O(n) space complexity to O(n) space complexity, right? So what we can do is we can store something. We can store the values in 2 variables. Let's suppose ending at 0 and ending at 1. And then we can use these 2 variables to create new ending at 0 and new ending at 1. And then we can assign these values back to these values and move forward, right? That's what we were doing for this particular case. We had these old values with which we created these new values. And then we moved forward, and then we had these 2 old values with which we created these 2 new values. And at the end of it, we just added both of them and gave the answer. So my answer in this case would be EA0 plus EA1, right? Let's try to code this and see if it works. So over here we have our IDE, and the very first thing that I want to do is create a scanner object to take in the input. And then we have a single input, which is n. So we can get this here. And then what we want is 2 variables, just 2 variables, which are EA0 and initialize with 1. Now, why are we initializing it with 1? We are initializing it with 1. If you remember, our base case was when the size is 1, the number of digits would be 1 and 1 each, right? And if we add them up, we would get 2, which is for 0 and 1, right? So we have our base case over here. So if I write this under comment, this is our base case when equal to 0, 1, right? So now when we traverse, if our base case is at 1, we have to traverse from 2 to n, right? We have to calculate for lengths 2 to n, as length of 1 is our base case, which is already handled. So I would have a loop which would run from 2 till n, and what I want to do now is to create new variables, right? So as we discussed, there would be a new ending at 0, right? And ending at 0 would be equivalent to ending at 1, right? So the previous state ending at 1 is my answer, right? I could only add 0 to all the digits that are ending at 1. And then we have new ending at 1, which is equivalent to ending at 0 plus ending at 1, right? After assigning values to these two variables, what I have to do is relocate the value to the old variable. So my ending at 0 would become new ending at 0, and my ending at 1 would become new ending at 1, right? And after this for loop, my answer would reside in ending at 0 and ending at 1. All I have to do is add them up together and I would get my desired output. So let's take a variable total, which would have my answer, which is ending at 0 plus ending at 1, right? And I just have to print this now. So if I print my total, right, this should give my answer, right? So on line 22, if I comment over here, this is my traversing and solving portion, right? And in line number 23, what we are doing is adding up all the strings, right? So these are the 3 steps that we have performed. Let's run this and see if it works. So it does. We are getting 21 for our sample test case. Let's submit this for all the test cases. So all the test cases are passing. We are getting 10 out of 10. That means our solution is absolutely correct. Now, this is the exact solution that we discussed. So I don't think there is a dry run that is needed. If you want to dry run this again with me, then you can go back in the video, and this is the exact dry run that we did, right? So there is no change in the dry run. If you want to try this question with the recursion, then you can. And the last thing that I want to discuss about this question is the time complexity. So what would be the time complexity of this question? We solved this question in just a single for loop. So the time complexity was O of n, right? And what was the space complexity? As we had discussed, the space complexity that we earlier had when we were discussing our previous approach using the arrays, it was O of n. But then we used the fact that we are using only 2 steps at a particular time, and we brought down space complexity to O of 1, right? Constant space. Okay, so I hope it was clear. I hope you liked the video. Please like, share, and subscribe. I will see you in the next video. Bye bye.